Good evening, everybody. Welcome to week 11 problem solving session for this course on regression analysis. I am Shreya, one of the TAs for this course, and today I'll be discussing problems with respect to week 11 lectures, which is basically focused on polynomial regressions. So let's get started. So first things first, till last lecture we learned a lot about dummy variables. All right. So we learned a lot about dummy variables, when to use dummy variables, how to use dummies, and what are the considerations, how many dummy variables we should use, so on and so forth. Now, till last week, whatever we discussed was with respect to a linear model with x's having that demonstrated a linear relationship between x and y. Okay, so to put it simply, so far what we have learned is okay, so from so far what we have learned, if yes, so yeah, one second. So far we have modeled a relationship between x and y where even in simple linear regression or multiple linear regression we could fit a straight line. Okay, this doesn't look straight. We could fit a straight line to the model. Okay, in when let's say we are having 2, so we are sort of, if this is x1, this is x2, and we have points scattered like this, and this is y, we sort of added a plane or something. Okay, so whatever we did, we had y equal to some beta naught plus beta 1 to the power x to the power 1 plus beta 2 x to the power x1 to the power 1, x2 to the power 1, and so on. Okay, extending this concept, now let's say if we have a relationship like this, something of this sort. So here in this case, you see, if I plot a line and if I plot some sort of a curve, then I think this is a better fit. than the green line. Okay, now equation for this blue line, it could be something like this. Okay, y equal to beta naught plus beta 1x plus beta 2x square, something like this. Okay, so instead of x and x to the power 1, we are fitting higher orders of x to match with the non-linearity of the data. Okay, now be very careful. This model is still a linear model. And why is that? Because we always talk about linearity in terms of the parameters. So here we see beta naught, beta 1, beta 2. These are all linear. So this one is actually a linear model with higher order polynomials in one, or it could be two variables. Okay, one or more than one variables, that is to say. So what is actually polynomial regression? Polynomial regression is thus a model like this. Okay, y equal to beta naught plus beta 1 x1 plus beta 2 x2 plus beta 1 1 x1 square plus beta 2 2 x2 square. Okay, let's say this one plus epsilon. This is one example. Of a polynomial regression. Okay, this could be a second order polynomial regression. Why second order? Because the highest order in the x's terms is 2. Okay, this is one example of a second order polynomial regression in two variables, x1 and x2. We could also have something like this, beta 1 to x1 x2. Okay, that would also encompass a polynomial regression. Okay, but what in the lectures we have focused is actually don't know why I keep getting logged out. Very strange. Alright. So, where was I? Yes. So, this one this is a polynomial regression in two variables. Now our focus was actually on polynomial regression in one variable. Okay, so if we are only focusing on one variable, then the model is something like this. This is y equal to beta naught plus beta 1 x plus beta 2 x square plus so on and so forth plus beta k x to the power k plus epsilon. Okay, so here if I have to write it like this, usually how do I write a regression equation? A multiple linear regression. Y equal to beta naught plus beta 1 x1 plus beta 2 x2 plus beta k xk plus epsilon. So here xj is actually equal to x to the power j for all j equal to 1 to k. Alright, so this is actually a second order model. Okay, beta 1 and beta 2 are beta 1 is actually the linear effect parameter. Beta 2 is called quadratic effect parameter. Alright, so this is how a polynomial regression in one variable should look like. Now, one very important consideration while talking about polynomial regression is the order of the polynomial. Sorry. So, one important consideration is actually order. Okay, so how to choose order? And the answer is order should be as low as possible. So usually what happens is that if we have some sort of, if non-linearity is detected, step 1 will be to try some transformations to make it linear. Okay, so we learned about a lot of transformation. We learned about log linear model, we learned about log model, we learned about transforming x to 1 by x. We also learned about some other forms of transformations like box-Cox transformation. So we should try, the first step is we should try such transformations to make the relationship between y and x linear if it is possible, because usually these polynomial or higher order fits are not that encouraged. Okay, so if step 1 fails, okay, then we'll go to step 2. Then we'll fit a polynomial regression with k as low as possible. Alright. And why is that so? Because we need our regression models to be generalizable. Okay, it shouldn't work for one specific case. So if let's say there are endpoints in our data, so a polynomial of degree n minus 1 can always pass through those endpoints, right? But then if we do that, if we fit such a model, that will not necessarily be a good predictor. Okay, that will tend to sort of overfit the data, and we don't want that. We want a regression equation which is fairly generalizable. So that is the reason why too high an order is not what do I say, is not recommended. Okay, fine. So once we have the order in place, the next thing is how to build the model. Okay, so we have decided that the order is going to be, let's say, it's already decided that k ideally should be less than or equal to 2. Okay, now the next question is, how do I fit or build the model? So the strategy is actually forward selection. We learnt about forward selection a couple of weeks ago. So what do? First we'll fit this thing. Okay, so if this is not fitting the data well, we'll incorporate this, and then we'll test beta not equal to 0 versus beta 2 equal to 0 versus beta 2 not equal to 0. If this is significant, okay, then we'll add more terms until the subsequent terms become non-significant. So what I mean to say is that first we'll fit this, then we'll add a square term. Okay, let's say beta 2 is significant, then we go ahead and add another term, that is beta 3x cube, and test for significance of beta 3 equal to 0 versus beta 3 not equal to 0. If beta 3 is also significant, we'll proceed to beta 4. But let's say beta 3 is non-significant, then we'll stop the model there. Alright, so here, let's say here we have this y equal to beta naught plus beta 1x plus beta 2x square. So beta 1 is significant, beta 2 is significant, and beta 3 becomes non-significant. Okay, so at this stage we see that this becomes non-significant. Then the final model will be this one, y equal to beta naught plus beta 1x plus beta 2x square plus epsilon, and we stop there. Alright. Now, another very important consideration while fitting polynomial regression is the problem of ill conditioning. Now, what do I mean by ill conditioning? So, and where does this problem arise? So, the thing is, in a linear regression, y equal to x beta plus epsilon, okay, the assumption is that the rank of x is actually equal to p. Okay, if we have, let's say, if beta is a p cross 1 vector, then rank of x should be p in order to have this x transpose x inverse. In order to have a unique inverse, we need to have a full rank matrix. So if rank x equal to p, we'll say that it's a full rank matrix, and then we'll get a unique x prime x inverse. And then, as we know, beta hat equal to x prime x inverse x prime y. Alright, this is one condition that we have. Now, what happens is that if, let's say, as order k increases, okay, x prime x becomes ill conditioned. And what do I mean by ill conditioning? Okay, so the thing is, this x prime x will not be or may not be accurate, and parameters will be estimated with error. To be very specific, if x or x's lie in a narrow range, okay, if this is the thing, that the x's are lying in a very narrow range, then ill conditioning will increase, and we'll often observe multicollinearity in the X matrix. Okay, so if you see that x, the range of x is 0.1, 0.15, 0.2, 0.3, and then if you compare x square, x cube, and then you find out the correlation between x and x square, then you will see these will actually have these may actually be quite large. Okay, so in such scenarios, if so we know if multicollinearity is there, then we have certain problems. Even if it is not perfect, even if near perfect multicollinearity exists, what were the problems? The standard errors will be high, tests will not be accurate. Okay, the tests of hypothesis. And then also what do we have? We'll have broader confidence intervals. So some associated problems that will arise. So ideal situation is not to have multicollinearity in the data. Okay, so this can happen if we take too high an order. So this is also another logic why we should constrain the order and keep it as low as possible. Okay, fine. Now another consideration that we have is, let's say, while fitting a polynomial let's say first we decide k to be equal to 2. Alright, we have decided that k will be 2. Now let's say we decide that let's try k equal to 3, or let's try k equal to 4. So at each step, if we fit normally, then what do we have to do? We have to re-estimate each parameter at each step. So this is computationally difficult. Okay, so in order to circumvent this problem, one way out is to have orthogonal polynomials. Okay, so why do we use orthogonal polynomials? The advantage is that we need not estimate we did not re-estimate the previous coefficients. Okay, only the new coefficient added has to be calculated. So this is more hassle free. Okay, because every time so what happens is that during any sort of modeling, chances are that we'll go back and forth quite a lot of times. We fit one model and then that will not suffice, then we move on to a higher order and so on and so forth. So these things keep on happening. Now if every time we have to re-estimate our parameters, then that is not something we would like to do. We would rather have a model where if we have fit a polynomial up to a certain degree, then we have the coefficients. If we wish to add another coefficient to the data, we just want to put in that extra amount of effort to estimate that extra parameter. We don't want to start everything from scratch. Okay, so if this is the preferred way to be or way to go, then orthogonal polynomials come in very handy. Okay, so nowadays, with the advent of softwares, it doesn't seem like an issue, but previously, when everything was calculated by hand, then starting everything from scratch was very time consuming and a laborious process nonetheless. So this was of more relevance, I would say, when we did not have softwares. But even now, if we can just manage and estimate the extra parameter, what's the harm in that? Okay, so yeah. And also, if to some extent, where is it? Yes, to some extent, ill conditioning can be tackled in some scenarios by orthogonal polynomials as well. Okay. Oh, I forgot to mention, how do we sort of how to get rid of ill conditioning? So the way out is centering the data. Okay, so instead of y equal to beta naught, we'll fit y equal to beta naught x minus x bar okay, and then beta 2 x minus x bar square plus beta 3 x minus x bar cube, and so on. In that case, we'll see that correlation between x minus x bar and x minus x bar to the power k might be low. Okay, so this is one way how we can tackle ill conditioning. Alright, now we were talking about orthogonal polynomials. Alright, so what do we do here? Instead of, so this was my original model, let's say beta naught plus beta 1 x1 plus beta 2 x2 plus beta k xk. So here, since xk equal to x to the power k, we'll rewrite this entire thing. This will be x plus x square plus x to the power k. Okay, so instead of that, we'll transform our model to something like this. We'll have y equal to alpha naught plus, or rather alpha naught p naught x plus alpha 1 p1 x plus alpha 2 p2 x plus alpha k pk x. Alright, where p u x is actually a uth order polynomial in X. Okay, and how is it defined? It is defined such that why is it we are calling it orthogonal. Summation P R xi into PS xi, where I runs from 1 to n, should be equal to 0, where R is not equal to S and R and S span from 0 to K. Okay, and P not X is actually always, xi is always 1. Okay, so if we formulate our model in this manner and then we write our model matrix as this, that X is nothing but 1 1 1 1, and instead of x1 x2 x3, here we'll write p1 x1, p1 x2, p1 xn, 2 pk x1, pk x2, and pk xn. Alright, so if we do this, then we'll have x transpose x as summation. So this is actually p naught x1, okay, 1. P naught x2 is also 1. So we'll have here p naught square xi, that is essentially equal to n. And since PRPS, if R not equal to S, then any pairwise cross product terms will be 0. So we'll have zeros in the off diagonals and only elements in the diagonals. Okay, like this one, the second one will be p1 square xi, third one will be p2 square xi, and the last one will be pk square xi. Alright, so then inverse of this is very easy. It will be 1 by this thing, 1 by this thing, 1 by this thing, 1 by this thing, and that's it. Okay, and instead of betas, we are going to have the parameter as alpha. So alpha naught, alpha 2 to alpha k. Okay, why? Because we are having a kth order polynomial. Alright, so then how much will alpha j come to? So alpha j hat will actually be equal to x prime x inverse x prime y. Okay, so if we simplify this, then each alpha j hat will be actually equal to summation I equal to 1 to n p j xi into yi divided by summation pj square xi, I equal to 1 to n. Now if I want to add an alpha k plus 1 hat, then again similarly we just need to calculate summation I equal to 1 to n p k plus 1 xi into yi by summation pk plus 1 square xi, I equal to 1 to n. So in this process, we do not need to choose, or we do not need to recalculate alpha naught to alpha k again when we decide to add a term alpha k plus 1 into the model. Alright, so if alpha j is this thing, then variance of alpha j will also be sigma square into x prime x inverse. So this would be sigma square by summation pj xi I equal to 1 to n pj square xi. Sorry. Okay. Alright. So how do I get sigma square? Sigma square hat will be actually the mean square error, or rather ms residuals of the model. Fine. Also, we have learnt that the residual sum of squares, that SS residual, is actually SS total minus summation j equal to 1 to k alpha j hat into summation I equal to 1 to n pj xi into yi. Alright, so this was already done in class. So SS regression is actually alpha j hat. So SS regression is actually, we can write it as, we can actually partition it as SS regression alpha 1, SS regression due to alpha 2 plus SS regression due to alpha k, where SS regression for each alpha j hat, sorry, here I'll put hats, is actually equal to alpha j hat summation I equal to 1 to n pj xi into yi. Which is equal to, so substituting the value of alpha j that we got from here, this is actually equal to summation pj xi yi I equal to 1 to n whole square divided by summation pj square x I equal to 1 to n. Okay, why? Because alpha j is also this thing, summation pj xi yi by summation pj square xi. Alright, so then if we go ahead and draw the ANOVA table, we'll have our sources of variation here. Next we'll have our degrees of freedom, then we'll have sum of squares, then we have our ms. Alright, so it could be alpha naught, alpha 1, alpha 2 to alpha k, and then the residuals. All these df's will be 1 and residuals will be n minus k minus 1 because of k plus 1 parameters that we are estimating. So we'll have ss due to alpha naught hat, ss due to regression, till ss due to regression till alpha k hat, and then ss residual, and then corresponding ms regression due to alpha naught. It will be equal till here, and this will be ms residual by df of residual. Okay, so why is this important? Okay, coming back to the initial question. So in this way, if we fit a model, we need not bother for other terms, number one. Number two, we can just focus on the newly added term, get the estimates, get the sources of, get the sum of squares due to regression, just because of addition of that variable. Okay, we need not recompute x transpose x again and again, and so higher order polynomials can be fitted very easily. And if we are building the model, let's say whenever we go for forward selection, what are we doing? We are actually testing every time, right, that which model will be a good fit. So we are proceeding sequentially. We are starting with k equal to 2, then moving on to k equal to 3, k equal to 4. So if every time we have to recalculate and get the estimates, then it becomes a little difficult. But with this method, we can easily keep on adding terms until we are satisfied with the order of polynomial, keeping it in mind that the order should be kept as low as possible. Okay, now once we have this ANOVA table, we can just proceed to test for significance of any of the alphas. So how do we do that? To proceed to test for significance, the h naught is actually alpha k equal to 0. So here one thing that we should keep in mind is that testing beta k equal to 0 is equivalent to testing h naught alpha k equal to 0. Let me write G. Okay, so if we are trying to find out if a jth order polynomial will be good or not by forward selection, so testing for each of these coefficients is equivalent to testing for alpha j equal to 0. Alright, so if that is the case, then we will use the test statistic f equal to SS due to regression alpha j by SS residual for k order of the polynomial n minus k minus 1. Okay, and this will follow an f1 n minus k minus 1 under h naught, and our rejection rule will be, will reject h naught if and only if f is greater than f critical 1 n minus k minus 1, and critical is actually 0.05. that is, the critical point will be upper alpha 0.05 point of an f distribution with df's 1 and n minus k minus 1. So this is how we should test for beta j equal to 0. Alright, okay, so given that, so what we have learned is that if xi's are equally spaced, then tables of orthogonal polynomials are available, and these polynomials can be easily constructed. Okay, so the assumption is what? Xi's are equally spaced. So if this can be ensured, then we would have p naught x equal to 1, p1 x equal to lambda 1 x minus x bar by d. Okay, p2 is lambda 2, let's say x I minus x bar by d whole square minus n square minus 1 by 12. Okay, p3xi also has some form. Okay, and so on and so forth. Okay, so for the sake of exams, you don't need to memorize all, but it would be good if you can memorize up to p2xi. Okay, till this, if you can remember, then that would be great. Now note, if x's are not equally spaced, then can we not consider or construct orthogonal polynomials? The answer is that no. We can always construct an orthogonal polynomial even if x's are not equally spaced, but that has not been discussed. But please know that even if x's are not equally spaced, orthogonal polynomials can be constructed. But this has not been explicitly discussed in our lecture series. Okay, so this was all that we learned about orthogonal polynomial, ill conditioning, order of a polynomial, and so on. Alright, now the other thing that we learned also during this week was one second. Yeah. Yes. So we also learned about something called piecewise polynomial, or in other word, splines. Alright, so how can we do that? Piecewise means what? So when do we use piecewise polynomial? So sometimes a lower order polynomial may not provide a good fit. Okay, so we could increase the order of the polynomial, but that may or may not increase the fit of the polynomial. Okay, so in order to make the regression better, we can fit polynomials piecewise, okay, like in segments. If we do that, then there are cases where people have seen that the fit is actually increased. I mean the goodness of that fit is increased. Okay, so what is actually what can be captured by a spline? So let's say in different ranges of x, the function behaves differently. Okay, so let's say you have something like this. This is your y versus x. So here if we look at this graph, okay, there could be many ways of fitting. The most simple is a linear fit. Okay, this is actually a linear fit, is we can see not good. Now let's try a quadratic fit of sorts. Okay, so let's say something like this. But here also we can see that this is not good. Alright, so instead of fitting an overall polynomial, if we can identify shorter segments and fit different polynomials to those shorter segments of the data, then what essentially we are doing is actually we are fitting piecewise polynomials. So in this example, if you look very carefully, if we divide the data, let's say into three parts, 1, 2, 1, 2 and 3 or something like this. Okay, so here maybe we'll be able to fit let's say we fit a graph like this. In this area we fit a straight line, and in this area we again fit another quadratic equation or something. Okay, so then these small segments, these lines, so this one, and these segments are actually my splines. Okay, and the joining areas like this one and this one, these are actually called knots. Okay, now how to partition? Okay, so we have to fit splines, that is polynomial of order k, again keep k as low as possible. Okay, and as few knots as possible. Okay, and each segment should have at least 4 to 5 points, otherwise it doesn't make any sense. If one section has 3 points and I am fitting a polynomial of order 2, that will be like an exact match, and that is not at all generalizable. So at least 4 to 5 points should be there in each of the segments of the data. Okay, so this is how we actually fit a polynomial regression, or rather piecewise polynomials, or in other words we call them splines to our data. Alright, now So with that context, okay, we also learnt quite a lot about polynomials, polynomial models in two or more variables. Okay, so as I was telling initially, if we have cross product terms, let's say something like this, beta 1x plus beta 2x1 x2 plus beta 1 x1 square plus beta 1 2x2 square, sorry, beta 2 2x2 square plus beta 1 2x1 x2. Okay, so then beta 1 2 is actually my interaction effect parameter. Okay, and we call this function or this equation as the response surface. Okay, and linear terms are this one, beta 1 and beta 2. Quadratic terms are beta 1 1 and beta 2 2. Alright, and now if we have to test H naught contribution from linear terms, then we'll test H naught beta 1 equal to beta 2 equal to 0. Okay, to test for contribution from quadratic terms, we test beta 1 1 equal to beta 2 2 and also the interaction beta 1 2 equal to 0. So how do we do this test? We use the extra sum of squares technique. And what was that? To remind you, so F will be SS regression full minus SS regression restricted by MS residual full, or in other words, SS residual from the restricted minus SS residual from full model. Okay, and this one divided by R, that is the number of parameters that we are testing. So in here R equal to 2, here R equal to 3. Alright, so this will be SS residual restricted, SS residual full by R divided by ms residual from the full model. Okay, so this is how we carry out test of significance for contribution from linear or quadratic terms. Right? Fine. All right, so with that we are let's move on to solve a few problems. So here the question is that fit a second order model to this data using orthogonal polynomials. Okay, so let's try and do this. So here in the first question we have this data observation x and y. We have been asked to fit a second order model to this data using the orthogonal polynomials. Alright, so what is the least square estimate of alpha naught? Okay, so from here what do we know? So alpha naught hat coming back to here is so alpha j is this one, so let us just write it down here. Alpha j hat is actually summation how much? Pj xi yi by pj square xi. So this is pj xi yi by summation pj square xi equal to 1 to n. Okay, now p naught xi is actually always 1. Okay, so then this is alpha naught hat is actually summation I equal to 1 to n yi by n, that is equal to y bar. So let us just find out what y bar is, and that is our answer. So we have 335 plus 326 plus 316 plus 313 plus 311 plus 314 plus 318 plus 337 plus 345 divided by 10. So this sum actually comes to 3243. So the least square estimate is 324.30. All right. Okay, moving on. Consider the data in problem 1. The least square estimate of alpha 1 is approximately equal to how much? Okay. So here let me write it down. Alpha j hat is equal to summation I equal to 1 to n pj xi yi by summation I equal to 1 to n pj square xi. Okay. Now going back to the example, you see here x's are equally spaced. Okay, so we note x's are equally spaced with d equal to 25. Okay, this is quite evident. Difference between subsequent x's is 25. All right, so once we have this, we can write p naught x equal to 1. p1x was how much? Equal to lambda 1 x minus x bar by d. Okay, so for this one, let us just find out x minus x1 by d. Okay, so here if we have x like this, so I'll just write all right. And how much is x bar? Let me just calculate x bar. Plus 75 plus 100, 50 plus 75 plus 100 plus 125 plus 150 plus 175 plus 200 plus 225 plus 250 plus 275 divided by 10. So x bar is actually summation xi is 1625 so x bar is actually x minus x bar 162.5. So x minus x bar will be something like this. 50 minus 162.5. Minus 112.5. 75 minus 162.5 minus 87.5. Okay, 100 minus 162.5 says minus 62.5. 125 minus 162.5 is minus 37.5. Okay, 150 minus 162.5 is minus 12.5. Then we have 175 minus 162.5. This is again 12.5. Then again 37.5. Then again 62.5. Then again 87.5. And lastly 275 minus 162.5. This is 112.5. Okay. So x minus x x minus x bar by d is how much? That is 112.5 divided by 25. So this is minus 4.5. This is 87.5 divided by 25. This is minus 3.5. 62.5 divided by 25. 2 minus 2.5. 37.5 divided by 25 is minus 1.5. And 12.5 divided by 25 is actually 0.5. Okay, and then minus 0.5, then again plus 0.5 plus 1.5 plus 2.5 plus 3.5 plus 4.5. So we have 10 observations. Okay, so we had our y's, we had our x's, we calculated x minus x bar, we also calculated x minus x bar by d. And now once we have this, we have to get the least square estimate of alpha 1. So P1x would be lambda 1 into this thing. Okay, so this is x minus x bar by d. Now we have to choose lambda in such a way that this becomes an integer. So let's say lambda equal to 2, then this would be minus 9, minus 7, minus 5, minus 3, 1. Then again 1, 3, 5, 7, 9. Alright, this would be lambda into x minus x bar by d. So then this is actually P1x. Alright, so let us find out P1 into y and then P1 square. So this will be 81, 49, 25, 9, 1, 1, 9, 25, 49 and 81. And this would be minus 335 into 9, that is minus 3015, then 326 into minus 7, that is minus 2282, then we have 316 into minus 5, that is minus 1580, then we have minus 3 into 313, that is minus 939, then we have minus 1 into 311, that is minus 311, then we have 1 into 314, that is 314, then we have 3 into 318, that is 954, then we have 5 into 328, that is 1625, then we have 7 into 337, that is 2359, and then finally we have 9 into 345, that is 3105. So summation of that, 3105 plus 2359 plus 1625 plus 954 plus 314 minus 311 minus 939 minus 1580 minus 2282 minus 3015 is actually coming out to 230. Okay, so here this will be 328 into 5, so this will be 1640. So the total will come out to be 245, and this total sum will be equal to 330, and then alpha 1 hat will be 245 by 330, which is close to 0.74. So the correct answer is B. Alright, moving on. So what is the least square estimate of alpha 2? Now here I have already calculated alpha 1. Now if we have to calculate alpha 2, this one was x minus x bar by d. So here we'll have x minus x bar by d whole square. So this would be this into this. Alright. Okay. So this is x minus x bar by d whole square minus n square minus 1 by 12. Now we have to multiply it with some lambda. So if we choose lambda equal to 0.5, then also this remains an integer, so we'll do that into 0.5. Alright, so then this is 0.5 into this thing. Now we'll multiply this with y. So this is p2y, and then p2 square will be this into this. So then alpha 2 is p2y by p2 square, which is 2.79, and that is this. Alright, so what do? We have x, we have y, we get x minus x bar by d. We take x minus x bar by d from previous, the 2 whole square, n equal to 10, so n square minus 1 by 12 is actually 8.25, so we get 8.25. We choose lambda 2 equal to 0.5, and then p2 equal to 0.5 into x minus x bar by d whole square minus 8.25, and then we get p2 into y and p2 square. Then we take a sum of these two columns, and then alpha 2 is actually equal to summation p2y by summation p2 square, which comes out to be 0.279, which is option C. Alright, so moving on. Now consider the data in problem 1. Sum of squares due to regression for parameter alpha 1 is approximately equal to, so sum of squares due to regression, what was the formula? It was summation pj xi yi whole square by summation pj square xi. Okay, so this was summation pj xi yi whole square by summation pj square xi. Okay, so for alpha 1, this would be summation pj square xi. How much did we calculate for alpha 1? So for alpha 1, this was 330. Okay, so this will be 330, and summation pj xyi was how much? This was 245. So this would be 245 square by 330, and that is 245 into 245 divided by 330. So this one is 181.893, which is option C. Alright, moving on. SS regression for parameter alpha 2. Alpha 2 is how much? Same, summation pj xi into yi whole square. So p2 xi into yi whole square by summation p2 square xi. So coming here, p2 square xi was 132. So this would be 132, and summation p2y was how much? It was actually 369. Okay, so this will be 369 square, and that amounts to 369 into 369 divided by 132. So this is 1031.52, which is option A. Okay. Okay. Moving on. Okay. So for this one, SS residual is actually SST minus SS regression due to alpha 1 minus SS regression due to alpha 2. Okay, so this is summation yi minus y bar whole square minus this is 181.89 and this one was 1031.54. So this is 1031.54. If you calculate, this will come out as 1240 minus 1 minus 181.89 minus 1031.54. This comes to be 26.67, and that's the answer. Alright, so moving on. So for this problem, the full model is this: y equal to alpha naught plus alpha 1 p1x plus alpha 2 p2x. Okay, so df of the error is n minus 3. Alright, and restricted is y equal to alpha naught plus epsilon plus epsilon. Okay, so F statistic is SS regression for full model minus SS regression for restricted model by MS residual of the full model and by the number of parameters tested. So here it will be 2, or in other words, SS regression for here, SS regression of the full model is 181.89 plus 1031.54, and SS regression for the residual model is actually SST. Sorry, SS regression is actually 0 because no explanatory variable is there. So this will be 0 by 2 by MS residual full. So that will be 26.67 SS residual divided by n minus 3 is 7. So if we do this, 181.89 plus 1031.54 divided by 26.67 into 7 divided by 2, we have 159.24, which is the correct answer. Alright, so moving on to the last question for the day. Can the second order term be deleted from the fitted equation? So for this, we have to test H naught alpha 2 equal to 0. So here again, we have to do SS regression full minus SS regression restricted by ms residual full. Okay, and this will follow F1 7. So SS regression full is 1 0. So then full model is the usual one, and restricted is y equal to alpha naught plus alpha 1 p1 x. Okay, so SS regression full minus SS regression rest is SS regression due to alpha 1 by ms residual full. So that will be SS regression due to alpha 1 was how much? This was 181.893. So this is 181.893 by 26.67 by 7. So this one is how much? This one is 181.89 divided by 26.67 into 7. So this was something close to 47.74. All right, and if we look into the F table, okay, so here df17.05 so here we see df17.05 is 5.59. okay, so f17 0.05 is 5.59. So since this one is way more than this one, so we reject H naught. Okay, and what was H naught? Therefore we reject H naught alpha 2 equal to 0. So what does that mean? Can we delete the second order fitted term? We cannot, because it is so significant. So answer is no. All right, so this was all for this week, and thank you so much for joining, and I'll see you next week. Bye.